Welcome to the Space Telescope Public Lecture Series. Tonight's talk, Understanding the Formation and Evolution of Galaxies by Cameron Hummels of Caltech. I'm Dr. Frank Summers, your host, and as always, I want to thank our amazing tech team, Thomas Marufu and Grant Justice. Our upcoming talks in July, on July 5th, we will have exoplanets, orbital mechanics, and the Death Star by Mia Bovell of Texas Christian University. Actually, she might change her topic by then. This is just one she gave me as a placeholder. We'll see what she actually comes up with. But if she does do that, it'll be really cool. On August 2nd, we have the talk you've all been waiting for, Webb's First Look. Images and spectra from NASA's newest great observatory. Alex Lockwood from here at the Space Telescope Science Institute. Yes, the James Webb Space Telescope will be it is currently producing its first images, taking its first spectra. You'll hear all about them on August 2nd, okay, here in the Public Lecture Series. On September 6th, we have First Light, unveiling the properties of galaxies at cosmic dawn, from Guido Roberts Borsani at the University of California, Los Angeles. Want to know about these things? Go to our website, www.stsci.edu/public-lectures, or just look for Space Telescope Public Lecture Series in your favorite search engine, and you will find this page. On the left, you can see we have the links to our webcasts, both on the Space Telescope webcasting site, as well as on YouTube. And on right, we have a handy dandy little box where you can enter your email address, push the subscribe button, and you will get our monthly emails. Also on the website, we have, of course, links to our upcoming lectures, as well as you can also look at our previous lectures. And when you click on one of these lectures, you get the full details, including the description. And if it's in the past, you get a link to the Space Telescope webcast, as well as the YouTube recording of it. For email, the announcements, as I said, just sign up at our website. You can also just subscribe to our YouTube channel, youtube.com/Hubble Space Telescope. It's all one word. And when you subscribe, you will get notices of new videos and reminders of live events, such as the one you're watching right now. Finally, if you have comments or questions, you can send them to the email address publiclecture@stsci.edu. For our social media, we run the social media for the Hubble Space Telescope, for the Webb Space Telescope, and another set of media for the Space Telescope Science Institute. Yes, our social media team is a busy group. They are on Facebook, they're on Twitter, they're on YouTube and Instagram. In contrast, I am not much of a social media person. I'm not a busy person on this, but if you want, you can find me on Facebook and Twitter as Dr. Frank Summers. Our news from the universe for June 2022. Story tonight, comet nuclei, the largest of the small. So when you think of a comet, you should think of this. However, I know that I'm talking to the general public. So when the general public thinks of a comet, yeah, they probably think of this. It's going to crash. It's going to hit the Earth. It's going to cause catastrophic planetary devastation. Considering this has only happened once in the last 65 million years, at least the planetary devastation phase, it's probably not the first thing you should think of when you think of comets. But hey, it's what makes it's what Hollywood likes, because it gives it a good plot line. What you should be thinking of when you think of comets is this, okay? So this is Comet Hale-Bopp, and you can see that it has a head to the comet and tails to the comet. It actually has two different tails, the dust tail, which is pushed back by radiation pressure from the sun, and the ion tail, which is carried back by the magnetic fields in the solar wind. So there are actually two tails to a comet. And the head, you can see, is pretty much fuzzy. All right, and that is what we call the coma. And this is comet Borisov observed by Hubble. And you can see, by even with Hubble's resolution, you can still just see the fuzzy stuff. Okay, this is way down deep inside that coma, but it's still just fuzzy part of the coma. All right. In order to actually see what the comet really is, the comet nucleus, well, you need to fly there. This is from the Giotto mission in 1986, which flew past Comet Halley. This is a wonderful picture of the nucleus of Comet Halley. Sometimes we call these giant snowballs. And you can see that where the sun is hitting it on the left side, the jets of material are evaporating away, okay, because the ices are sublimating and spraying away in these jets. We have done this for several missions. I have to say my favorite comet nucleus that we've seen is Comet 67P Churyumov-Gerasimenko, which is only 3 miles across, not very big, but I like it because it's a contact binary. All right, you got 2 pieces, and it earned it the nickname Comet Rubber Ducky because it kind of looks like a rubber duck. All right. So this montage was released a few years ago from somebody at NASA, putting together all of the various comets that we visited. And you can see, at least in this montage, the biggest one here in the center is Comet Halley, and that's only like 9 miles across. So now enter Comet C 2014 UN 271. Okay, that's just the catalog name. Okay, comets are given names of their discoverers, but really to their catalog names are much more relevant for astronomy. And so this comet was discovered in archival images from the Dark Energy Survey. And what's really intriguing, it was discovered when it was about 3 billion miles away. And that's about the same distance as Neptune is from the sun. Usually we don't see comets until they get inside the orbit of Jupiter. So this is way out there. Therefore, it must be really big in order to be bright at such a large distance. What we're looking at here are Hubble observations, and these came a little later when the comet had gotten to about 2 billion miles away from the sun, about the same distance as Uranus is from the sun. So this is, this is a very bright comet. But we also have improved our computer modeling, all right? So what they were able to do is take the Hubble observation and from it create a model of the coma, all of that fuzzy gaseous stuff around the comet nucleus, and then subtract that off from the observation to give us an approximation of what the emission from the nucleus looks like. So this is an approximation with computer modeling of the nucleus. Now, is that big enough to be able to, is that fine enough to be able to tell how big this nucleus is? No, actually not. But if you combine it with radio telescope observations, I believe these are from ALMA, the Atacama Large Millimeter Array, combine those observations with the Hubble observations, then you can get an estimate for the size of the nucleus. And this, they find, is about 85 miles across. So now we look at some of the larger comet nucleuses. All right, and on the right, we have C 2014 UN 271. In the middle, you can see Hale-Bopp is estimated at like 46 miles across. And on the left, you see Comet Halley, which this diagram says 7 miles, but everything I found online said 9 miles. So there's a discrepancy here. And you may say 85 miles, that's not that big still. All right, well, it's big. It's actually bigger than the state of Rhode Island. Yes, to scale, that's the state of Rhode Island. If you didn't know, Rhode Island is only about 50 miles from top to bottom, okay? So we got comets that are bigger than the entire state of Rhode Island. Another important thing to do is make a comparison of what size comet you need to create that planetary devastation we talked about before. Okay, so it says something about the size of comet C 2014 UN 271, and it also says something about the size of Rhode Island. Okay, so it's looking at in that planetary devastation phase. Here's a little sign that says you must be this tall to cause planetary devastation. The comet that the asteroid that hit in Chicxulub that led to the downfall of the dinosaurs 65 million years ago was about 10 to 15 kilometers across. Now, that was an asteroid, and asteroids are denser and can have more mass per unit volume. So on comets, as we talked about, as Cameron just mentioned, are considered dirty snowballs and are a little puffier, less dense. So we're not exactly sure how large of a comet you need to cause planetary devastation, but this is the range of which they are. And so these studies are important to understand just how big these comets can be. What was the initial distribution when the solar system formed 4.5 billion years ago. And it's a great collaboration using both the Hubble Space Telescope and radio observatories on the ground to be able to measure these tiny, tiny objects way out in the solar system. Okay, so our speaker tonight, I'm very happy to have him here. You've already met him, Cameron Hummels. Cameron got his PhD at Columbia University in New York City. And he has done postdocs at the University of Arizona and is now at Caltech. As you will see from him tonight, he does galaxy formation simulations. The kind of research I did 25 years ago when I was doing research before I turned my career to purely doing outreach. But he also is working on not just the galaxy formation, but also the material around it, what we call the circumgalactic medium. And it's one of the things that always intrigued me because, I mean, the visible galaxy is really kind of small, and the material that's infalling, because it never stops infalling, is way out there. And so he's doing really good simulations on that, on visuals and understanding that. He's also very much into doing outreach to the public. While he was at Columbia, he served as the director of outreach for Columbia University. And when he got to Caltech, he sort of created the position of director of outreach and put himself into it. So I like people who appoint themselves head honcho on this. He does, a lot, like we do, public lecture series stuff. He also does stargazing, and he does Astronomy on Tap, which will feature me as a payback for him doing my series. I'm doing his series next week. And I guess one last thing to say about him is he's heavily into outdoors. And in February, which is what, 4 months ago, he did 170 miles across Death Valley in 4 days without any support. He's not allowed to use roads. He's not allowed to have food caches. He's not allowed to have, somebody come along and help him out and do all stuff. He had to do it solo, as if he was the only person on Earth. And not only did he do it, he set a record time. So a man who has the endurance to get through anything, even these technical glitches here, ladies and gentlemen, Dr. Cameron Hummels.
Awesome. Thank you very much, Frank. I'm really excited to be able to talk to all of you about one of my passions, which is galaxy evolution. And hopefully I can convey some of what I find exciting to all of you in the next 45 minutes or so. So thanks for this opportunity. So as you're seeing here, this is a beautiful visualization of a supercomputing simulation done by my colleague, Dr. Nathan Goldbaum at UC Santa Cruz, showcasing the evolution of a Milky Way-like galaxy. You can see a lot going on here. It's, for the most part, all real scientific phenomena and realistic as to what one would see. The one discrepancy is that time is passing really, really quickly in this simulation relative to what it would be in reality. About every second in the simulation is on the order of like 20 million years passing. So it's really evolving quite quickly, but the white points represent individual stars. The pink regions represent H2 regions that are ionized gas clouds surrounding supernovae and star forming regions. And this is really a good representative of what our Milky Way might look like as it evolves over time. But let's start at the beginning before we get into galaxies per se, and start with a little bit of history relative to what we've learned in the last few hundred years about galaxies and why we think we know what we know. So first off, I'll just give this general question to all of you guys. What do we see when we look up in the night sky? Now, this is normally when I ask people to shout out the responses, but since I can't hear all of you, I mean, I guess I can look at the YouTube comments, but since I can't hear you, I'm going to guess that you're shouting out things like stars. Stars are pretty obviously the things that you see when you look up in the night sky. Also, people might shout planets. We see planets. Of course, most of the planets, the visible planets are up in the early morning, which is far too early for me right now. But we also see the Milky Way, and hopefully, I realize a large portion of the general population, especially in Western countries, doesn't have the opportunity to go outside of a city and perhaps see from a dark sky site. If you have the opportunity, I highly recommend it. And one of the things that's really majestic when you get in a dark sky site is the opportunity to see the Milky Way. Here you can see it, kind of a glowing band across the sky. This is from Joshua Tree National Park near Los Angeles here. This is a more representative view, more all sky view of that. And you can see that there's a lot of structure here, but for the most part, the name seems apt, right? The Milky Way looks like a band of milk across the sky. But make no mistake about it, it's not milk. It's actually composed, and this was understood reasonably early, the last few hundred years, that the band of light actually is composed of many, many individual distant stars. But because they're so far away and thus quite small on the sky and so numerous, they blend together into a band of light that looks like an extended light source like milk. And you can also see dark regions here. These are dust lanes. So it isn't that those regions are devoid of stars or starlight. It's just that there's intervening dust that's absorbing the light between the background stars and us, the viewer, and gets absorbed along its way to us. We also see this kind of behavior in other galaxies, but I'm getting ahead of myself. So this was an early representation before photographs of a drawing, because if you can't take a picture, you do the best thing. You look through your telescope and you draw things of what of the Milky Way looks like. But more modern images, like seen here on left by the Gaia mission, which has been operating for the last 10 or so years, we can really see a lot of the structure in this. And it was understood quite early. It was actually proposed by the philosopher Immanuel Kant that the three-dimensional structure of our Milky Way is something like what you see on the right side, where there's like a disk of material with a bulge of material in the center, and that we ourselves, the Earth and the Sun and the rest of the solar system, are about halfway out in that disk. And thus, because we're present in the disk, we can't look down, face on the galaxy in the same way that we can in other galaxies, but what we see is just this band of light across the sky. And that three-dimensional structure is held up to our observations of other galaxies and seems like a reasonable representation. Okay, so going back to the original question of what do we see when we look up in the night sky, and tying into what Frank was just discussing, we see comets, much like this comet that you can see here. Now, as you could tell from some of the naming schemes associated with the comets that Frank was describing, comets get named typically after the person who discovers them. And so historically, that was kind of a way that people could become famous by being the first to discover a comet and then having that comet named after themselves. Now, in order to discover a comet, it has to be before other people have seen it by nature of you discovering it. And what that means is that it's not going to be big and bright, because then it would be obvious and other people would have seen it probably before you. So if you're going to be the first person to identify a comet, it's going to be very, very faint in the outer solar system, as it hasn't yet approached close enough to the sun to be bright. And it'll just be kind of a faint smudge that isn't easily discernible by anyone but perhaps you. Now, there was a comet hunter known as Charles Messier in the 18th century in France, and he was determined to discover comets. But it turns out that there are a lot of other things in the night sky that aren't comet-like, that aren't faint little blurry smudges on the sky that you could easily confuse with a comet. The difference with a comet is it hasn't been seen in that location before, and it will eventually move across the sky relative to the background objects. But these other objects that might be confused with a comet tend to stay put. And so essentially what's kind of ironic is that Charles Messier is not known for discovering comets. He's known for identifying these non-comet objects that would be easily confused with being a comet. And these sorts of objects are known as the Messier list or the Messier catalog. And they're amongst the most beautiful and bright objects that you can see when you look through a telescope. These are obviously modern images that are taken with modern technology, but they reveal just some of the beauty associated with them. So these are things like, you may have heard of the Orion Nebula or the Pleiades cluster or the Hercules cluster or the Ring Nebula. And again, if you have the opportunity to get to a dark sky-ish site and look through a telescope, you'll probably be looking at one of these objects because they're really spectacular. So you can see from this kind of representative list, there are 110 different objects, and you can see from the list that there are a variety of different kinds of things. You can see some things that are very obviously star-like. So this is the Pleiades cluster. You might also know it from the Subaru logo, because that's the Japanese word for this star cluster is Subaru. But it's a star cluster and very obviously composed of individual stars. Similarly, the Ring Nebula. Nebula is just a famous, like a fancy word for cloud. The Ring Nebula is a cloud of gas, again, associated with a star. We can see individual stars present, like the white dwarf in the center of this nebula. And that cloud is glowing, and it's associated with that. But then there are these kind of, at least 100 years ago, or a couple hundred years ago, there are these kind of cryptic objects called spiral nebulae. And you can see that it's a little bit harder to discern what these objects are. They have some sort of spiral structure, but you can definitely make out that they seem to be a little bit cloudy. And you can see some stars that are present, but it's unclear if those stars are associated with the object or they're foreground stars or whatnot. And so this is the Great Andromeda Nebula, Messier object number 31. And what was unclear was, are these objects nearby, like stars, in our own Milky Way galaxy, or are these distant objects that are, they called them potentially island universes, which is to say objects much like our own Milky Way galaxy, but much, farther away. And at the time, we thought that for the most part, the universe was, like the Milky Way was the extent of the universe, because that seems enormous. I mean, that is enormous, right? The extent of the Milky Way disk is 30,000 light years away. That's a huge distance, right? So to think of things that were even beyond this at kind of unthinkable distance and themselves Milky Way-like structures was almost unthinkable. But this was essentially identified in this thing called the Great Debate of 1920. So you had an astronomer representing the idea that these are nearby objects within our own Milky Way and associated with individual clouds and quite small, as in the size of like a solar system or maybe slightly larger than that. Or you had another person representing that these objects were island universes, much like our own Milky Way, and they were very far away and they were very, very large. And much like most debates, whether they're philosophical or political or sometimes scientific, there wasn't really a winner to this debate. And it was unclear what is the nature of these spiral nebulae. And so time went on, and people were trying to identify how to resolve this debate. And really the way to resolve it is to determine the distance to these spiral nebulae, because if they're close by, then they're small, and if they're a long ways away, then they're large. But it turns out that determining distance to objects in space is actually really challenging. I mean, we get kind of spoiled, right? Like when I walk along the street, I can tell that something, a signpost is 20 feet in front of me, or if it's like a couple miles in front of me, because how do we have depth perception? We have depth perception because we have two separate eyes. We use something called the parallax method, although most people aren't familiar with this term, but it's the fact that we have two eyes from slightly different positions that are both cameras that are looking at some distant object, and we can kind of interpolate its distance from geometric means, although it's all done internal to our head. But I'm going to ask everyone, it's kind of a goofy experiment, but I think it's really illustrative. So if you can follow along at home and do this, I think it'll be helpful. I want everyone to hold up a thumb in front of their head, as goofy as it seems. And then I want you to close one eye, so like wink at it, and look at your thumb, and then switch, so you're opening that eye and closing the other eye, and just kind of go back and forth. And what you'll notice is your thumb appears to change position relative to the background objects behind it. That is essentially the parallax method for determining distance. If you move your thumb closer and do this again, your thumb will appear to move more relative to the background objects. And essentially what we do to determine distances to objects in space, rather than just your thumb in front of your head, is to do the same thing with observations of nearby stars. So on the bottom of this cartoon, we have the Earth in its orbit around the sun. And on the right side, we see where the Earth is in January. And then on the left side, in 6 months later, it's where we are in July. Now, we're trying to observe this nearby star kind of in the middle of the screen. And when we look up at it in January, we see that the nearby star relative to the background stars here at the top of the screen puts it on the left side of those, as we can see here on this left kind of inset panel. Here's our nearby star, and it's on the left side. But if we wait 6 months and then observe that same nearby star relative to those background stars, we see now that it's on the right side of those stars, simply due to our change in position over those 6 months as we orbit around the sun. And so you can see this exact same thing that we just did with our winking at our thumb to see its change in position. This is how we determine the distance to stars. But it only works for stars that are reasonably close to us, hundreds of parsecs, although now with more sensitive missions like the Gaia mission, we can do this out to a few thousand light years away, which has really opened up the precision with which we can measure distances. But it's really the basis with which we determine the distance to objects. But it's far too, stars need to be much, much closer to us than was possible at the time when people wanted to do this 100 years ago. So determining distance to more distant objects in space was really helped a great deal by this scientist Henrietta Leavitt, this prominent astronomer at the Harvard Observatory in the early 20th century. And she identified this ingenious method for determining distance. She identified a special kind of star called a variable star. Not all stars are this, it's some small subset of stars, but there's a decent number of them in the sky. And what happens is they pulsate in size, and they change their brightness. And so they'll go from being bright to being a little bit fainter, to being bright, to being a little bit fainter. And there's a very set period over which this oscillation takes place, on the order of a few days. It'll be bright, and then a couple days later it gets faint, and then a few days later it gets bright, and so on and so forth. And that in itself is kind of interesting, but the thing that makes it a really useful technique is that the period over which that oscillation occurs is directly tied to the intrinsic brightness of the star. It's like it prints out that it's a 100-watt light bulb or a 1,000-watt light bulb, because essentially the problem all boils down to this. If I walk out of my house at nighttime and I look across the street and I see a light there, I can't easily tell if it's a firefly that's 5 feet in front of my face, or if it's a spotlight that's 2 miles down the road that's pointed at me. But with this method, this variable star, if I can observe that star pulsing, then I know its intrinsic brightness, and by looking at its apparent brightness, I can put those two things together, and I can back out the distance to that actual object, which is incredibly useful. And so a person with whom you're probably familiar, Dr. Edwin Hubble, who the Hubble Space Telescope, of course, is named after, employed this technique that Henrietta Leavitt had identified with the Mount Wilson 100-inch telescope right here in our backyard outside of Pasadena. And at the time, it was, for about 40 years, it was the largest telescope in the world. And he pointed this telescope at at the Great Spiral Nebula in Andromeda, and he identified some stars associated with that nebula, and he's found some of the stars were variable stars, and thus he was able to determine the distance to the Great Spiral Nebula in Andromeda, and he identified that it was 2.5 million light years away, which was an enormous distance. I mean, it is an enormous distance. And what that told us is that really settled the great debate, and it said these objects are large and distant. In fact, much, much farther away than we ever really, like I said, it's kind of unthinkable at the time that these things are as far away as they are, and that each of these indeed is much like our own Milky Way galaxy. And so these were redubbed, instead of spiral nebulae, they were called galaxies. And that was really kind of the birth of our understanding of galaxies about 100 years ago. So thank you, Edwin Hubble, for that wonderful contribution. And just to continue a little bit on Edwin Hubble, that wasn't the only thing that he's known for, of course. He's also known for identifying that those distant galaxies are actually traveling away from us. This is a cartoon showing that. Again, this is us in the Milky Way, kind of in the center of this plot, although not necessarily the center of the universe. And he identified that each of these galaxies is traveling away from us. And the ones that are farther away from us are traveling faster away from us, which is kind of weird. Like, why is everybody running away? But it turns out that there's a pretty reasonable explanation for this, and it's not that we're the center of the universe. It's simply that the universe itself, like space itself, is expanding. And so it isn't that we're special here in the center of the universe. If you were in any of these galaxies, you would observe all those other galaxies traveling away from you as well, because it's the space that's expanding, not that everything's like just moving within that space away from us. And the example that oftentimes gets used for this is, imagine you have, you're baking a blueberry muffin in the oven. Now, of course, you have your dough, and it's all runny and doughy, and it has little blueberries in it. And when you put it into the oven, you turn up the heat, the yeast that's present in that dough starts to expand, causing the dough to expand, much like here, space is expanding. So from the perspective of any blueberry in that leavening blueberry muffin, the other blueberries are moving away from it, not because they're actually moving away, but because the dough itself is expanding between them and the other blueberries. So I think that's a pretty apt analogy that's good for visualizing what the heck is happening. And that's not the only piece of evidence that we have for the Big Bang. There are a number of different pieces, but that was kind of the first and a very strong, suggestion of what's going on and why the universe behaves the way it seems to be behaving. This is just a plot that was from Edwin Hubble's paper, because it's nice to show actual scientific results. On the x-axis, this bottom line is the distance away that a galaxy is from us. And on the y-axis, it's the speed at which it's traveling away from us. And all the individual dots are galaxies. And you can see that as you go farther away from us, the dots are higher up, meaning that they're traveling faster away from us. And this is constraining the rate at which the universe is expanding, called the Hubble expansion, or the Hubble constant. Everything gets named after Hubble because he did so many contributions, but it really is kind of worthwhile and really transformed our idea of space. So that's how, I'm a big fan of Edwin, and that's how you get a space telescope named after you. So good job, Edwin Hubble. Okay, so yeah, here we are, the Hubble Space Telescope in the flesh. Hopefully, long live the Hubble Space Telescope. I use it a lot for my research, so hopefully it will continue to operate for a long period in the future. So a quick summary so far of the history of what this all is. There's a lot of stuff in the sky, including these smudges that were originally called spiral nebulae, which we now understand are actually galaxies like our own Milky Way galaxy. The universe is enormous. We see these galaxies a long ways away from us, and we see on the order of like 200 billion. Well, we see on the order of 100 billion, but we think that there's probably 200 plus billion of these objects in the sky, and that the universe is expanding and getting even bigger with time. And then, yeah, Edwin Hubble's pretty cool dude. Okay, so we've talked a lot about what galaxies, what they aren't, but what are they? This is an image that you may be familiar with. Every Apple Macintosh computer had this as its background for a period in the past, and it's kind of an edited version of the Andromeda Galaxy. They took some artistic liberties in making this image, but nonetheless, this is a galaxy, and this is actually a proposed image of what our own Milky Way galaxy looks like if we were looking down on it. You can probably make out this little label here for Earth. The Earth and the Sun and the solar system, we believe, is about halfway out in the disk, and it's in one of these spiral arms. We can talk more about why we believe that later on. But what is a galaxy? Really, it's just a collection of stars and gas. So the light that we see is coming from individual stars that, as I said, oftentimes blends together into that Milky Way band across the sky. There's also dust that's present. And it's quite large. You know, there's like 100 billion stars or so, and it's around 100,000 light years across in terms of the disk itself. But you can obviously tell that there's some rotation and spin associated with this object just based on the spiral, and that is true. We can measure the spin associated with our own galaxy as well as other distant galaxies. And much like any rotating object, there has to be a force that's holding it together. If you get on a carousel or a merry-go-round and it starts going too fast, you're going to fly right off the side, right? So there has to be a force that's holding this together, or else it'll just fling itself apart. And that force is gravity. So let's really quickly just talk about gravity since it's so important. Gravity, everyone has an idea of what gravity is. It's the force that holds us to the Earth, but it holds us to the Earth from regardless of where we're standing on the Earth, because it's an attractive force. Not only are we being pulled down to the Earth, but we're pulling back. The Earth is getting pulled back to each and every one of you, although it's not a very high magnitude force because we ourselves don't have a lot of mass relative to the Earth. But really, gravity is just an attractive force that pulls any two objects that have mass towards each other, and that mass increases as they get closer together and as those masses increase. And that was identified by Isaac Newton around 400 years ago, one of his major contributions to the world of astronomy and physics. So that's how gravity works. So gravity is really the force that's holding galaxies together, but it turns out, so it's a gravitationally bound collection of stars and gas. But it turns out if you count up all the stars and gas in a galaxy and figure out how quickly it's rotating and how much gravity, like mass, needs to be there to hold the galaxy together, it's not enough. It's not enough by a long shot. It's like some galaxies, it's too low by a factor of 10. Some galaxies, it's too low by a factor of 1,000. There's some unseen mass that needs to be present to hold the galaxy together at the rate at which it's spinning, or else it would fling itself apart. And that unseen mass is referred to as dark matter. And that discovery was made largely by Vera Rubin. There's a new telescope coming out named after Vera Rubin, the Vera Rubin telescope in Chile. And we see this in basically all the galaxies out there, that there's not enough mass that's present in their visible components to hold them together, which is why we have to invoke this unseen, mysterious dark matter. We can talk a lot about what dark matter is and what dark matter isn't, but right now the kind of paradigm is that dark matter is some sort of subatomic particle like an electron or a proton that happens to weigh quite a bit but doesn't interact through electromagnetic or nuclear forces. It only interacts gravitationally. But this hasn't yet been like confirmed, but it's super, super hard to detect these things because they only interact gravitationally. So stay tuned. Hopefully that's a problem that will be solved in my lifetime, but it's definitely a hard problem. Okay. So what do we know about galaxies from observations? Here's a famous image that people are probably familiar with called the Hubble Ultra Deep Field. It was an image taken of a very long exposure image taken of the sky, a small region of the sky. And every image in this particular, or I'm sorry, every object in this image is a galaxy. And you can see a huge diversity in the types of galaxies that are present. You see, you know, this kind of whitish spiral galaxy. You see very blue objects. You see very red objects. You see kind of ellipses, kind of weird looking things. This looks a bit like tadpoles. I mean, there's all kinds of stuff going on here. And so astronomers have come up with a taxonomy to kind of break this down and classify these into different types. So the main types, there are two main types that people really break it down into, and that is red ellipticals. You can see there's like a reddish tinge to these systems, and it's an elliptical because it looks like an ellipse. Now, I tend to think of things in food analogies because I like food. So I think of these in terms of eggs. It looks kind of like a hard-boiled egg. It's just a single component. And keep in mind, the glowing light that we're seeing is starlight. All that light is stars that are very distant and numerous and kind of blend together, but they make up this kind of elliptical-looking structure. Similarly, the other major type are blue spirals, much like the Andromeda Galaxy is, or the Milky Way is, and it has a bit more structure to it. There's the disk component with the spiral structure, and then there's the bulge in the center, which is kind of like, well, again, going back to the egg analogy, it's kind of like the yolk in the center of a fried egg. So you've got your flat disky component, and then you've got your yolk as the bulge in the center. And again, that's all starlight. It's just stars on different orbits that make up these two, like yolk and disk component, or bulge and disk component. And then there's kind of a catch-all category that catches the things that aren't red ellipticals and aren't blue spirals, and that is the irregular galaxies. And these are just all sorts of morphological types, all manner of weird shapes. They tend to be very blue, and I just refer to those as scrambled eggs because they're just a mess, and they just don't easily fit into those two other categories. So you can see examples of this in the Hubble Ultra Deep Field, but we definitely see this, these three different types when we look up in the sky at the, like I said, 100 billion or so galaxies that have been identified. But what else do we know about galaxies from observations? We know, you might naively just think that galaxies are randomly distributed through the sky, but it turns out that there's not. There's actually structure there. And this is a nice movie that was put together by the Sloan Digital Sky Survey visualization team, showing the distribution of galaxies in the sky. Now, obviously, we aren't able to fly through galaxies at this speed. This is superluminal speed, but you can see, but this is real data from this star survey and galactic survey. And you can see that galaxies are not randomly distributed. There's clumps, like this clump here, and then there's like kind of like rope-like structures. Here's like a rope of these things right across here. And where the ropes coincide, then you get nodes where there's a clump of material. And then there's voids kind of separating these filaments. And this is what's known as the cosmic web, because it looks kind of like a spider web, like a 3D weird, drunk spider made this kind of spider web. And it really describes the distribution of galaxies and thus the distribution of matter throughout the universe on very large scales. Yeah, this visualization is really great. I love this. So this is kind of a 2D flattening of the results of that. So each point is a galaxy. In the center is the Earth and the sun, and we're looking out into the universe. And you can see that it has this kind of web-like structure. You see filaments, you see kind of some two-dimensional flat sheets, and then you see where those filaments cross, you see clusters. And that's really describing the large-scale distribution of matter throughout the universe. But that's kind of weird, right? So, so what do we know about galaxies from observations alone? Well, we know that these are groups of stars and gas and dark matter. They're gravitationally bound. There's a bunch of these objects throughout the universe. There's this huge population that's very diverse, but we can broadly break it down into ellipticals and spirals. And then finally, it has this weird web-like distribution in space. But of course, the question that arises from this is like, why, right? And observations alone, it's very hard to answer why this is the way it is, because the timescales over which galaxies change are very, very slow. If you think about the Earth and its orbit around the sun, it takes a year for the Earth to go around the sun. I mean, that's how we define a year, right? But like the Earth orbiting around the sun, our entire solar system, composed of the sun and the planets and the Earth and so on and so forth, is orbiting around the center of the Milky Way galaxy. But instead of it taking a year to make one full orbit, it takes like roughly 250 million years. It takes a very, very long period to make a full orbit. And that timescale is pretty representative of the timescales associated with these distant galaxies, just because they're so big and they're only moving so quickly. So, I can't see a galaxy and follow its evolution in real time, because I'm only going to live, well, I don't know. I'm not going to live too long if I spend that much time in the desert, but I'm only going to live, humans only live on the order of 100 years if they're lucky, right? And these things are changing over millions or hundreds of million year timescales. So we just don't even have the institutional, the civilizational memory to follow the evolution over these very long timescales from just observations alone. So I don't know if that galaxy is going to turn into that galaxy at some other point in time, just because we don't have enough time to watch it. Enter in theory and simulations to better understand how one galaxy might change to another galaxy and why. So this is the stuff that I do in terms of my research, and many of my colleagues do, and Frank was involved in doing as well. So how do we simulate physical systems in general? I'm going to apply this to astrophysics and galaxies, but in general, it's kind of like the scientific method. We write a computer program that represents some sort of virtual space inside of our computer, where we can, like a sandbox, where we can monkey around inside the confines of this virtual space. We'd like to include all physics that we can, but unfortunately, it would be computationally too expensive, and we wouldn't be able to make much progress, even running on the fastest supercomputers that we have access to. So we only can include the dominant physics that operates on these sorts of scales. Now, for these large scales in astrophysics, the main physics that we want to include are our good friend gravity, that we already talked about before, because that really dominates on large scales, and fluid dynamics. Fluids, like how the seas, the currents in our oceans operate, but also how our atmosphere, like gases, largely behave as fluids at high enough density. So the planets have fluid dynamics, and at the Trifid Nebula, other gas clouds throughout the universe. Much of the universe can be approximated by the fluid equations, in the same equations that approximate how water flows through a pipe. Then we create some sort of starting point for our simulation, some initial condition, initial distribution of matter. We run the simulation forward, accelerating time so it's faster than real time. So we can have, like, instead of a second, only a second goes by, a second can be 100 years or a million years go by. And then we do science with that. We analyze the results, we compare with observations, we see how well we did, and somehow that yields some sort of scientific understanding that might be better than we had previous to this happening. Oops. So let's simulate galaxies using an initial condition of just a really simple distribution of material. We already talked about this kind of schematic of a Milky Way or a disk galaxy having a disk component like a fried egg, and then having a bulge component like the yolk part of a fried egg in the center, and it all be stars. Let's just take two galaxies and fling them into each other. That sounds fun. Just, cause mayhem and see what results. Now, I'll just mention that the visualization that I'm about to show was done by our very own Frank Summers, of course, the host that's hosting me tonight, and it's one of my favorite visualizations. So we're taking these two simulations, we're flinging them together, and then periodically, like now, we're going to fade to an actual image taken with the Hubble Space Telescope of an irregular galaxy. And you can see that even though this is a reasonably simple simulation, we're going to rotate the simulation around and then fade to actual data taken with the Hubble Space Telescope. And you can see obvious similarities between the behavior in this very simplistic simulation and actual images of very complicated galactic structures. And it's really eye-opening, because before that, you see these irregular systems and you're like, what the heck are these weird shapes? Why do they have weird shapes? Why are they blue in color? And yet these are reasonably easily modeled by a very simple two galaxies slamming together that provides us a really good explanation of how to form these. These are just galaxies that got too close to each other, they slammed into each other, they interacted. When they interacted, they caused a new burst of star formation. That new burst of star formation resulted in the kind of bluish color. New stars tend to be dominated by the most massive blue stars that are present in those populations. And you end up with these, a really good explanation for these blue irregular galaxies that are so obvious throughout the sky. So I really love that, for having this beautiful direct comparison between these a simple simulation and actual data that everyone is familiar with. Okay, so that was cool, but let's move to something a little bit more complicated. You know, it'd be nice, rather than starting out with two simulated galaxies where we've already formed them. Well, what about, let's start with nothing. Let's start with the beginning, just after the Big Bang, and see if we can actually form galaxies organically. So in order to do this, we need to start with initial conditions for our simulation that were like the early universe. So what does the early universe, what did it look like? Well, we have an idea of this. Remember our idea, our cartoon version of what the universe looks like with the Milky Way here and all these galaxies traveling outward away from us. Well, if we go back in time a little bit, you can imagine the galaxies that are traveling away from us are a little bit closer because they've been traveling away from us, right? And if you go back farther, they're going to be closer still. And you can keep going back until all the galaxies are kind of piled on top of each other. And that's the Big Bang for the most part. I mean, that's an oversimplification, but that's roughly the idea to why we know that there was some sort of origin time at which the universe kind of began, this Big Bang moment. And it turns out we do have some images of what's known as the light echo of the Big Bang. Now, these are not at the moment of the Big Bang. These are a few 100,000 years after, but that's a very short time scale relative to the amount of time that's taken place since the Big Bang, which is a few billion years. This is called the cosmic microwave background. You're probably familiar with it if you've read anything about astronomy or cosmology in the last 50 years. And this describes the distribution of radiation and thus the distribution of matter very shortly after the Big Bang took place. And so in this, I don't want to get too bogged down in the details of this, but in this, the red regions are very high overdensities relative to the background level of material. And then the dark blue regions are underdensities where there's less material relative to the background. And if we plug this in, this matter distribution, into our simulations as our starting point for the simulations and run it forward, we get something like this. This is a simulation that I ran a few years ago, and it shows the distribution of material over the course of the universe from just after the Big Bang to present. Now you can see that this cube is very white because everything's very uniform, roughly uniform in the early universe, just perturbed by these slight overdensities and slight underdensities. And then as we move forward in time, the overdensities and underdensities start to be accentuated by gravity. Remember, gravity is an attractive force. So if you have a bunch of mass, if I have a bunch of mass, I'm going to be effective at pulling more mass into me. And it's kind of a rich gets richer kind of game, right? Because if I pull more mass into me, well, then I'm more effective at being able to having more gravitational attraction and pulling more mass into me. So it's like a snowball effect. And what ends up happening is you very naturally create this distribution of matter that we saw earlier, this cosmic web of stuff, where those overdensities seed gravitational infall of the surrounding material, and you form clusters and sheets and filaments describing the distribution of matter on very large scales. And you know, that's awesome. This doesn't even require fluid dynamics. This is just gravity, and we can reproduce the distribution of the cosmic web that we're able to see in observations like the ones that we saw earlier from the Sloan Digital Sky Survey, that we see the same sort of distribution. And it's like a wonderful explanation that could only be revealed through simulations and theory like the ones that I showed. Now there's additional movies like this wonderful visualization done by the Illustris team and Mark Vogelsberger and collaborators at at Harvard and MIT and Max Planck and a variety of other institutions, showing, again, you can see in dark purple this kind of filamentary structure connecting connecting galaxies. All these little points are galaxies. These little yellow points are overdensities in the material, in the matter along these filaments. And where those filaments cross, that's where you have galaxies and clusters of galaxies that start to build up with time. And this visualization is just incredible. It's like cinematic. In fact, I wouldn't be surprised if Frank Summers were involved with this. So just really nice visualization of how the distribution of matter changes over time and how you have this very cosmic web buildup of material simply by the presence of gravity, much like we see here with the Sloan Digital Sky Survey. So if we zoom in on individual systems within those filamentary structures, this is another simulation that I was involved with, the fire simulations that are PI'd by Phil Hopkins here at Caltech, one of my collaborators. And the left side is going to show, you can see that filamentary structure. We're going to zoom in on one galaxy in that and watch its growth over time. And this white expanding circle represents kind of the sphere of influence, the kind of the gravitational region over which that galaxy dominates. And you can see that it's growing over time. Again, we're doing the entire evolution of the universe here in like 30 seconds. So this is a very sped up version of the growth of this galaxy. But this is thought to be a galaxy much like our own Milky Way galaxy. I'll play this again. But you can see this filament, and you can see lots of the individual galaxies, and essentially they're falling into this galaxy over time. And this brings up what often people refer to as this kind of morbid analogy that galaxies are cannibals. They grow by eating neighboring galaxies that fall into their gravitational field, and then they just kind of consume them. And that's how it works. It's a people refer to it as a hierarchical construction of galaxies. You have two small galaxies, they fall together, they grow into a larger structure, then those structures fall into larger structures and into larger structures still. And that's how we see the remnants of galaxies in our galaxy that have been slowly shredded and torn apart and added to our own Milky Way. But we see this in our galaxy, and we see this in other galaxies. Now, if we take that same simulation from the fire simulations and we process it to make a visualization that's more representative of what you'd see from starlight and dust and gas, this is what it looks like as it evolves over time. So again, this is a Milky Way-like galaxy that we've simulated in our computer. And you can see that it looks reasonably realistic relative to a lot of the observed galaxies that we see. Right now, we're flying through the disk plane of the galaxy. You can see there's a lot of blue starlight, but then there's these red patches. Those red patches are from dust that's absorbing the light that's passing through it. So you see them kind of as a void. This can be a little bit disorienting here as we're backing away from this spiraling kind of pulsing galaxy. But this is kind of state of the art with representative to how we're modeling these systems and how well we're doing in comparison to the systems that we see when we look up with telescopes like the Hubble Space Telescope. These are some stills from the fire simulations, and you can see these look reasonably realistic compared to actual observations of actual galaxies that we see in the sky. Now, of course, that's not what we're doing. We're not just trying to reproduce and make them look similar. This isn't like movie making here. We're building these galaxies from first principles, from computer simulations where you code in all the physics that you think is there. We're starting from these cosmic microwave background initial conditions and running them forward and iterating by adding additional physics here and additional physics there to better understand how these galaxies are matching what we see in the sky, not just by appearance, not just by size and structure and color, but also by their composition, by their magnetic fields, by the distribution, by their temperatures, by the types of stars that reside within them, all of these things to better understand not just can we reproduce the ones that we see in the sky, but we control all the knobs on these. So we know if I can reproduce one that looks like one in the sky, then I can look, oh, okay, so the magnetic field strength is this, or the distribution of material, or the metallicity that's present in that galaxy is this, when that might not be so readily observable by those galaxies just because they're hundreds of thousands or hundreds of millions of light years away from us and not easily identified in that capacity. So, and then lastly, the last simulation that I'd like to show is close to home, because it's our own Milky Way galaxy and what's going to happen to our Milky Way galaxy in the next few billion years. Now, earlier I kind of fibbed, because this simulation, I said all galaxies are traveling away from us, but I kind of lied. There's one galaxy that is not traveling away from us, and it's our old favorite, the Andromeda galaxy. So we've got the Milky Way up here, and down here we've got the Andromeda galaxy. Don't worry so much about the Triangulum galaxy for the purposes of this. But the Andromeda galaxy is actually traveling towards us, and in a few billion years, we're going to merge with it. The Milky Way will merge with the Andromeda galaxy and form kind of synthesize a new galaxy. And what's kind of ironic about this is that the individual stars in the galaxies, there's very little probability that they'll actually collide. It's just that because most galaxies are mostly empty space between the concentrations of matter that we call stars or planets. But over time, these things will coalesce into a single structure. And because astronomers have a good sense of humor, the resulting galaxy that will happen in the next 5 to 8 billion years, because it's the combination of the Milky Way and the Andromeda galaxy, we refer to it as Milk-omeda, which I really dig that. Should get that as my license plate or something. Anyway, so kind of in summary, based on this last section, what do we know about galaxies just from simulations alone? Simulations can reproduce many of the properties of galaxies. I mean, it's not perfect. We still have jobs. We still have a lot to understand about galaxies. But they form from small overdensities in the early universe, and gravity accentuates these overdensities and causes them to be the seeds for these galaxies that exist. And then slowly those galaxies kind of cannibalize their neighbors and grow to larger and larger structures by merging. You can have spiral galaxies that merge to make elliptical galaxies, much like the two spiral galaxies of the Milky Way and Andromeda merge to form kind of an elliptical system, the Milk-omeda system. And that will happen in the next 5 to 8 billion years. So don't sell your real estate. This isn't as dire as things like climate change or, oh heck, the COVID pandemic. I don't know, but this will happen. We are sure that we are traveling at each other. The gravitational fields from each other will interact, and we will merge, but it will be many billions of years from now. And then just the last thing that I want to talk about is on what sort of computers do we run our simulations? It is not, in fact, as you may have guessed, an old 8088 from decades past. These are supercomputers that we're using. So for those of you who have seen The Martian, which is an excellent film, young Donald Glover plays an astrodynamicist who works at NASA, the NASA Jet Propulsion Laboratory, and he does a particular calculation on a supercomputer called the NASA Pleiades supercomputer, which I was on earlier today. This is a real supercomputer. It exists I think it's at Ames up in the Bay Area, and they filmed on location. It's composed of, I forget how many, something on the order of 50,000 CPUs that are in these big racks, cooled, very cool to allow them to process. So this is all accurate. There are two things that are not accurate about that scene. One is you don't actually need to go to the place to plug into the computer to use it. We have something called the internet that allows you to connect to remote computers from pretty much any other computer connected to the internet. And so you can connect to this supercomputer from, like I said, I was on it on my home computer here earlier today doing some computational work. It's available if you have a NASA grant or work for NASA. You can apply for time on this supercomputer to do the calculations you need to. There are other computers that are provided by the National Science Foundation and so on and so forth, and you can apply for time to use them to do your bidding on whatever project you need to work on. And the other thing that isn't entirely accurate is it doesn't tell you at the end that your calculations are correct. You have to kind of know yourself that the results of your simulations are correct or not. It just does the equations. You have to figure out if it's correct. But other than that, the scene was reasonably accurate. So good job, 20th Century Fox and The Martian. So anyway, that kind of takes me to the end of my presentation. In summary, I covered a lot of stuff here, from the history of galaxies to the observation of galaxies to the simulations of galaxies, but kind of my bullet point highlights are here. And there's a bunch of visualizations you can see on my website. Again, I'm Dr. Cameron Hummels. I'm a researcher at Caltech in the astronomy department. And I'm happy to take questions, but one last plug, as Frank mentioned, I run the public education work at Caltech Astronomy. And if you're ever in the Los Angeles area or you live here, we have in-person events. We had our first in-person event last month. And we do stargazing lectures once a month. You can come to them. It's open to the public. They're all suited for public, much like this lecture series is here. We also have Astronomy on Tap that takes place at a bar. We're doing one this coming Monday. And as Frank mentioned, he's going to be speaking at it. And so you can come, drink a beer or whatever floats your boat and hear about science. And then there's astronomy themed pub trivia. And all of our stuff is recorded and live streamed on YouTube. So you can check that out too. So I'm happy to take questions. Thank you much for your time. And yeah, galaxies are awesome. Hubble's awesome. And stick with science. It's great.
I couldn't agree more, Cameron. Science has been a fantastic career for me. I really enjoyed it. And it looks like you really enjoy yourself as well.
I do. It's true.
All right. So that was a great overview of the initial of getting out to the scale of galaxies, and then lots and lots of information on how we understand galaxies are the way they are. I mean, that's kind of what we do in science. We go, hey, take a look at that. Why is it that way? Right?
Why is it that way? Exactly.
Exactly. And I just like to mention that simulations are sort of a third branch of astronomy, right? Think of the theorists who are doing equations and doing all that stuff. We think of the observers who are going out to telescopes and observing. But the connection between theory and observation is often the simulations, right? And I just wondering your perspective on that as somebody, because you got your PhD about 20 years after I got my PhD. So yeah. How has that evolved over the course?
That's a wonderful question, and it's really grown. So I did my undergraduate studies in computer science. I didn't actually study astronomy until graduate school explicitly. And I think that really, in some ways, prepared me for this a bit more than people who just studied astronomy or physics. But really, yeah, I think you're absolutely right that there's essentially three fields now, maybe even four if you count the people who build instruments, like the people who build the cameras aboard the Hubble Space Telescope or the James Webb Space Telescope. And so you've got, yeah, there has to be an interconnect, because there's only so much. Many of these physical systems are so complicated that it's very difficult to turn to pencil and paper and go to first principles and be able to make a lot of progress in trying to reproduce a real galaxy when you need millions or billions of computations in order to follow its evolution. So computers are good for that, but we can't rely entirely on them. We need the pencil and paper to boil it down to analytic principles too. So.
Right. I mean, computers can give you insights that you can then further explore with a theory and all this stuff. It's just it's just wonderful to see how it has grown over the years. Absolutely. All right. So let's bring in Grant Justice. We've had a good number of people on our chat tonight. Grant, you want to turn on your video and join us?
Absolutely.
Cool. Sure.
All right.
Yeah. Thanks. Twinsies.
we love the worm logo. So very glad that NASA brought it back. All right, so Grant, we've had some good conversation. What questions would you like to bring up for him?
Sure. First off, and I actually like this one because I'm interested to hear what you have to say about this as well. What is the bar in bar galaxies? What does it affect, and why don't all galaxies have them?
Oh, that's great. I'll do my best to answer this question. The bar essentially, okay, so just to make sure everyone understands what the question is referring to. We talked about a taxonomy of galaxies being spiral galaxies and elliptical galaxies, and then the catch-all that was irregular galaxies. Now, spiral galaxies can be further differentiated into barred galaxies or non-barred galaxies. And essentially what that means, the bar is a dynamical component that's an extension of the bulge in the center. Remember we were talking about, I made the kind of callus analog to a fried egg. It would be as though the yolk of the fried egg, the bulge of the fried egg, were kind of rectangular in shape. It were extended out into the disk and kind of rectangular in a bar. That is a dynamical effect that is caused. It's definitely an area of research, but it's caused by stars being in a particular orbit that holds that bar over time. Because remember, all of these all these components, like the disk of the galaxy or the bulge of the galaxy, it's stars. It's all individual stars that are just kind of decomposed into those compositional structures, morphological structures, and the bar is no different. So it's stars that orbit in a particular way to make those. And I'm trying to remember the thing that actually causes the bar. And I think,
so is it the instabilities and the what are those resonances?
Lindblad.
The Lindblad resonance, the inner and outer Lindblad resonances, right?
Yes.
So I mean, I remember that one of the first computer simulations that just tried to simulate a spiral galaxy almost immediately developed a bar instability, right? So it's a natural gravitational formation that occurs in certain setups.
But I'm trying to recall what causes the Lindblad, because obviously there are galaxies.
All right, quick, call Frank Shu.
Yeah, exactly. Like the Andromeda Galaxy that don't appear to have a substantial bar. I mean, we see systems like this, the Pinwheel Galaxy. There's a bunch of galaxies that you can see that it's more like a sphere in the bulge in the center as opposed to a bar. And I forget because I don't do a lot of galactic structure. I do more hydromodeling of why that's true. But yeah, you're exactly right.
It's okay. This is the caveat I give people. Is
that's all right. I'm 30 years out of graduate school. I knew it back then. Okay.
There's such specificity to what we study in astronomy that it's difficult sometimes to ask the right questions.
All the things.
Yeah.
Okay.
All right. And this is one, again, we actually have a public lecture that we did on this with Brandon Lawton, and he would go over the moon for this, but I'm asking you anyway.
Sure.
How empty are the empty regions in between the filaments? And what's the average-ish size of them?
That is excellent. Let me see. Obviously, there's some diversity. You know, there isn't just a set interfilamentary distance between objects or between these filaments. But the voids, people refer to them as voids, they tend to be quite empty. They're occasionally, there is a subfield of astronomy and galactic astronomy that focuses on void galaxies. That is to say, galaxies that find themselves in these kind of without any neighbors around to influence them either gravitationally or radiationally. So they definitely are, there's a significant deficit in the number of galaxies and the amount of matter that's in these void regions. Sometimes they're, it's a handful of galaxies. Sometimes it's even less than that. But the size of the voids, it's going to vary, but it's going to be on the order of, I'd say, like 20 to 100 megaparsecs, which is jargony. 60 million to 300 million light years across. Very, very large regions in between the clusters of galaxies and clusters and
one of the things that I always liked about watching the computer simulations of these galaxy things, everyone watches the structure formation and your formation of the filaments. I found that when I looked at them and I just watched the voids just sort of expand over time. Yeah. And if you look at the empty regions and not the dense regions, you really get a similar perspective. It's a counter perspective that has a lot of scientific insight in it.
Absolutely, because that stuff is getting flushed of its material as it's getting evacuated and going into the dense regions. And yeah, you see a similar growth of those as well. Excellent point.
Awesome.
Cool. Next question.
All right. What makes a galaxy similar to our own? Like, what kind of observable differences do you look for to identify it and say, oh, that's like this one or that one?
Broadly speaking, a lot of what I was talking about when I was saying this simulation is a Milky Way-like galaxy is that it's a spiral or a disk galaxy that's relatively well evolved, that there's active star formation going off in it in the spiral arms, much like we see in our galaxy or the Andromeda galaxy, and that it tends to be at a certain mass range. As you can imagine, there's a huge range continuum in the masses of galaxies that you see. Some are very small. We call them dwarf galaxies. Dwarf galaxies can be on the order of 1/100th of the mass of our Milky Way to 10,000th of that mass. Then we talk about ultra light dwarfs or ultra dwarfs that are even lower mass than that. So the Milky Way isn't the most massive galaxy out there, but it's on the higher end. It's considered a giant-ish, or I mean, we refer to them as normal because it's our galaxy, so of course it's normal.
Of course.
But something that's like a Milky Way galaxy or Milky Way-like, I would refer to as a spiral galaxy or a disk galaxy that isn't actively engaged in a collision with another one. Andromeda is a ways off, so we aren't yet engaged in it, or else it would look a lot like those pesky irregulars that we showed earlier. And it has on the order of 1 trillion solar masses of material, plus or minus, something on that order. So that's including its dark matter as well as the visible matter, the gas and the stars that are present in it.
It's always so easy to talk about this and just forget the scale of everything.
I mean, just 1 trillion. You just throw around.
Drop in the bucket. It's fine.
So 10 to the 12th solar masses of material is how we refer to it.
Or we just call it an L-star galaxy, right?
Or an L-star galaxy.
That's really getting into the jargon.
Yeah, I'm not going to get into.
No, don't go there. Don't go there. Grant, next question. Come on, quick.
Okay. How do spiral galaxies stay spiral? Do the filaments have like an angular momentum that they have to maintain in order to keep cohesion?
Great. These are all great questions. So
our online audience is awesome.
Yeah, people are on it. So, well, for one, angular momentum tends to perpetuate itself in the same way that if you have a merry-go-round that's spinning and without friction present, if it's a well-oiled merry-go-round, it's going to keep spinning for a long period of time. The same thing goes for galaxies. They're rotating. There are dissipative effects, but for the most part, it wants to keep going. But as you say, there's a torque. For the most part, galaxies, as you could see in the simulation where I showed it kind of zooming in on the galaxy and showing the other galaxies falling into it and it building up over time, each of those infalling galaxies is transferring torque to the galaxy itself, the one at the center. And so galaxies over time, at least we think from the computer simulations, may change the direction of their rotation, essentially the axis of rotation. So it's kind of like you have a merry-go-round that might be spinning like this, and then all of a sudden another galaxy falls in from this direction, and all of a sudden it torques everything, and now your merry-go-round is spinning like this. And so over time, due to the infall of other systems and other mass sources into this, it applies these torques and kind of spins up the galaxy to continue its rotation. But yeah, torques from other objects falling in along the filament seem to be the perpetuation of angular momentum and rotation in these systems.
And I'd like to mention one thing here that people don't often recognize is that the spiral pattern as it orbits around the Milky Way is moving at a different speed than the stars within it. Okay, one of the important things to note is that like our sun was born in a spiral arm, but it moved out and then moved into other spiral arms and around. So the stars orbiting in the Milky Way are moving into the spiral arms and moving out of those spiral arms. And the spiral arms have this pattern speed that is different from the orbital speed of the stars within it. And that's one thing that's always been fascinating. It's important to recognize because like our star is 4.5 billion years old, and it's made about 18 rotations around the center of the Milky Way. So it's orbited 18 times, and so there's a lot of interactions that it does as it goes into and out of these spiral arm regions.
The analogy that I like to use for that is like when you say something out of your mouth, you're causing vibrations with your vocal cords that are vibrating. They're causing acoustic waves, but those are vibrations of the atoms in the air around your mouth. And when someone else is standing across the room and they feel those vibrations in their eardrum, it isn't that the actual atoms that you vibrated with your vocal cords have traveled across the room and are running into the person's eardrum. It's perpetuating that longitudinal wave of basically a pressure wave through the intervening medium. And it's the exact same thing that Frank was talking about. There's this spiral density pressure wave of material in the disk, and we flow through it. The stars flow through it, but yeah.
Awesome. So that leads me directly into the next one.
Perfect.
When Milkdromeda happens.
Yes.
By the way, I do not like Milkdromeda as a title.
Oh, I love
I'm a thumbs down on that term. But anyways, go ahead.
When the Milky Way and Andromeda eventually meet, is gravity really the only force that is going to be affecting the momentum of the galaxies? Like, what other forces can be exerted on those spiral arms and those filaments?
Gravity will be the dominant one because, so for the most part, the forces that dominate on these very, very large scales, the galactic scale or larger than galaxy scales, are gravity, because it doesn't really cancel out very well. You could imagine, let's say a galaxy is charged. It has a net charge such that it repels other things of similar charge. The problem with that is macroscopic objects don't tend to remain charged with a net charge for very long, because they effectively attract the things of the opposite charge and it cancels it out. And so this is true of macroscopic objects in space as well. And so you can't imagine that there will be there may be we think that there are magnetic fields. We observe magnetic fields within galaxies, but the strength of those magnetic fields are hundreds of thousands of times less intense than our sun or the Earth. So they're very, very weak. They still do play a role in the evolution on from subtle effects, but they're not dramatic, and they're not, they may alter the path and the trajectory of ionized gas, plasma that's charged, as it falls through the galaxy. But I guess that would probably be the next thing that would be an influencing thing. I would say the main things that would influence kind of the evolution of the Milky Way Andromeda combined system would be gravity. And then the stars, for the most part, are just going to be falling along their gravitational trajectories based on the distribution of mass. And then the gas and the ionized plasma will follow a modified direction because of a few things: magnetic fields, as well as radiation. If there's an intense radiation field caused by a bunch of stars that get formed and are pumping out all kinds of light, visible or UV or X-ray, that can also alter the distribution of mass in the form of gas. But for the most part, those stars, the individual stars that have already formed, they're like little BBs, little bullets. They're just going to fly through and do their own thing according to the gravitational potential that's there, that's reasonably well described by Newtonian dynamics.
Right. And just to clarify that the hydrodynamics of the gas clouds colliding, right? Because
Yes.
the stars will pass straight through each other,
But
the
those
gas clouds will collide, they'll shock heat, will often create star formation, because that's what we see in starburst galaxies is the results of collisions. So, but on the largest scales, really gravity is just about it.
Yeah,
Okay.
and to take off on a little thing that Frank mentions there. So oftentimes I say, like, don't worry about it, we've got bigger problems, which is definitely true. And stars, we don't have to worry about like the Earth slamming into a star or slamming into a planet. But something that we do need to worry about is when the gas clouds that are present in those galaxies slam into each other, as Frank suggests, they're going to shock heat, and they're probably going to induce a bunch of new stars to be formed. Amongst those new stars, there will be massive enough stars that create supernova, and those supernova, when they explode, will not be great for us here on Earth. So it won't be a really good place to hang around in when that occurs in 5 to 8 billion years, because of the radiation field that's caused by these exploding supernovae. But on the other hand, like, we've got other problems to solve, like our sun dying in that time scale as well, and consuming the Earth. So we've got
a lot of the simulations have Earth being flung out to the edge of the galaxy and being all alone, way away from everything.
Saved,
We could be either in the intense of star forming region and have supernovae, or we could be out all alone, really, really cold out at the edge of the combined Milky Way Andromeda.
Different flavors of bad news.
Yes.
Okay.
Yeah.
We're getting
Have
down
time for a couple more.
Let's just do one more. I know we had a
One
little
more.
bit of technical problems, so we're running a little long, but it's already 9:30. So let's move. Let's get that one killer question to really hit them.
All right. So I like this one a lot, and I usually try to save this sort of a question for the end of the program. But what was your moment that got you involved? Not necessarily like it's your job or what have you, but what was your defining moment that interested you in astronomy?
I mean, there have been a series. I guess the one that most easily fits into this argument is, it's probably not unlike many people's trajectory towards getting into astronomy and space science. I had the opportunity to look through a telescope when I was like 11. There was an amateur group in a parking lot in an elementary school that was near my house, and I got to see Saturn, and it was super cool. So that was definitely like pointing me in that direction. But as I said, I studied computer science as an undergrad, and only later switched towards doing astronomy and astrophysics. And I don't know, I mean, I just always knew that I wanted to do science, because I think it's one of the most like interesting and kind of noble pursuits. Oh, I'm getting sunlight on me here. Noble pursuits that we can have is to better understand the natural world and our place in it. And, a lot of people give me a hard time, and they say like, well, what are the applications of this? How can you make money on this? And it's like, well, the main point that I like to make is, pure research going in lots of different directions, even without the direct application towards, this is going to solve this problem, or this is going to solve this problem. Better understanding the world around us is incredibly important, and takes us in directions that we could never have foreseen. In the 19th century, everyone thought that the dominant technology was going to be steam power. And if you were really worth your gumption, you'd go out and do research in steam power. But it was a kind of a nutty dude named James Clerk Maxwell playing around with magnets and prisms that figured out the theory of electromagnetic like interactions. That's basically, if you'd asked people at that time if he was doing something worthwhile, a lot of people would have said no, he's just wasting his time. And yet his work is the basis of all of 20th century and 21st century technology, in terms of how currents run through circuits, how fiber optic cables work, the internet, silicon, semiconductors. All of this is based on that work, and it's incredible. So I think I'm a huge proponent in doing scientific research for the point of better understanding the natural world, and the spin-offs will come from it, and it's impossible to predict where that's going to be.
How do you put a price on the betterment of your species?
Well,
what's that?
Yeah.
How do you put a price on the betterment of your species?
Exactly.
And I will just note that all of computer technology is based upon the Josephson junction, which we wouldn't know about unless we did quantum mechanics. And when they were doing quantum mechanics in the 40s, you never would have expected anything to come out of it. Okay. It was, it's the kind of stuff. So yes, basic research leads to amazing results, not next year, not next month, not 10 years from now, but decades down the line. And that's why basic research, we have to continue doing it. All right, Cameron, that was fantastic. I'm sorry we didn't have time to do even more questions. You can look through the chat on YouTube and see if there are other ones that you'd like to answer.
Yeah. Absolutely.
Next month, on July 5th, Mia Boble, current title for her talk, Exoplanets, Orbital Mechanics, and the Death Star. If you want to know what that is all about, come join us then. Until then, thank you all and have a great day.